Okay, we're going to get started. So today we're going to do some training. So would everyone please push mute the volume? Mute the audio, please. Okay, thank you. So today what we're going to do is we're going to build some tools that are going to be very useful in this class, but more generally. And they're some of the most powerful tools in general analysis of dynamic systems, but also in the analysis of particularly dynamic economic systems. They're going to help us to formulate some things. So we're going to talk about two things. We're going to talk about linear state space models, which are going to create the language and the framework within which we cast some celebrated models of tax smoothing and debt management. So my source, and then the second thing we're going to do is we're going to talk about consumption smoothing models. And this will be the modern version of the celebrated permanent income model of Milton Friedman, which has been refined in work by Robert Hall and other people. And we're going to, we'll learn that model, and then it's going to turn out that that model is isomorphic or mathematically equivalent with the Barrow tax smoothing model. So that's where we're going. And where I'm getting this material from is actually, so I can be a little fancy now because we have, well, I'll attempt to be fancy. I'll fire up Google, and I'm going to go to a website called Quantaconnet, and there's a set of lectures here. And actually, you'll notice up on top, we can actually print out the lectures. But I'm going to these lectures called in Python, which is a language. There I am in the Python lectures, and I'm going to be so this website. I'm involved. Several of us are involved in creating this. Is designed to teach two things at once: quantitative economics and computer programming. And we teach it with this free language called Python. So I'm actually going to be using, using a couple lectures here. I'm going to be using, there's linear state space. So if I pushed on that, there's a lecture I'm going to talk about. If I come over here later on, I'm going to talk about linear quadratic dynamic programming. That's the second. So you can find everything that I'm going to be talking about there, these two things. In addition, if you want a PDF of this, I'm just going to be marking up the PDF of this. So that's my source for today's lecture. So here you'll see I printed this out. We'll start with a great quote, which summarized. It's Marquis de Laplace, the great French mathematician and physicist. He said, "We may regard the present state of the universe as the effect of its past and the cause of its future." And this is a one-sentence summary of the Newtonian idea of the clockwork universe. That's basically summarizes the sophisticated models of dynamics until around 1900, when things changed. So we're going to talk about the state. So for us, finding the state is going to be an art. So we're going to use these linear state space models, and we're going to get a lot of profit from a little knowledge of linear algebra. Linear algebra is going to be our tools. I'm just going to go over. I'm just going to go over the first part of this lecture because it's going to be the part that I need. But actually, I recommend other parts because some of you might be interested in eventually learning about the theory of prediction. This lecture describes quite economically a powerful prediction, a theory of linear prediction, which is all cast in linear algebra. Okay, so why do we like? I'm just going to lead you through these notes and put some underline. So there's going to be a reader's guide to this. Okay, why do we like linear state space systems? Well, here's some of the reasons. It's got this theory of prediction. It's a workhorse for a whole bunch of applications. Some of you have heard of real business cycle theory. It's cast in the language of the linear state space system. It's useful for predicting geometric sums of future values of a variable like non-financial income, dividends on a stock, the money supply, almost anything of interest you can name. And it's going to be key ingredients of, well, here we are, Friedman's permanent model of consumption smoothing and Barrow's model of tax collections. That's what we're going to use it for. Okay. So now what we're going to do is, if you go to a baseball or football game, first thing you do is you get a program that tells who the players are. So I got to tell you who the players are. These are the basic objects. They're going to be the mathematical objects in place. So the first thing is going to be an n by 1 vector xt. So it's a vector of length n, and there's going to be one vector for each time. So there's going to be a sequence of vectors. And xt is going to be called the state. And what it's going to be a complete description of the current position of the system. A complete description of the current position of the system. And we're going to put that into this vector. And we'll give examples later. And the second thing is there's going to be an independent and an identically distributed sequence of normally distributed random variables. So WT is an m by 1. This is m by 1. It's going to be an m by 1 vector of shocks. These are going to be IID normal shocks. So if you go and you look up Wikipedia and you look up a Gaussian or multivariate normal distribution, that's what this is going to be. The mean, what this means is the mean is 0 and the covariance matrix is identity. And then the next thing is there's going to be a k by 1 vector. There's going to be a k by 1 vector called yt of observations. Those are going to be the things that we as the economists are going to observe, potentially. We may not see the state. It may be hidden. We may or may not see it. We'll see that later. And this is going to be a vector, k by 1 vector, and there's going to be one vector for each time. So notice there's a lot of bookkeeping going on here. Okay. So these have time dates on them. So xt, wt, and yt have time dates on them. And when we do dynamics, we're just talking about things that have time dates. That's all it means. Now, the key thing is there's going to be 3 key matrices. There's going to be an n by n matrix. Look at the dimension of this. A called the transition matrix. It's going to do a lot of work for us. There's going to be an n by m matrix called C. It's called the volatility matrix. You know, Rob Engel at NYU is famous for having something called a volatility institute. And it's all about this C and measuring C. Then we're going to have a k by n matrix G. It's called the input matrix. I'm sorry, it's called the output matrix. Okay. And so we're ready to talk about our linear state space system. Here's it going to be. It's going to consist of these the two equations, which we're going to stare at. These first two equations. This first equation is called, we could call this the transition equation, or the law of motion. And what it says is next period state is equal to the matrix A times this period state plus C, the matrix C, times the vector of shocks. That's it. And we've arranged things so that the multiplication of A and X is legitimate. We've made the matrices conform to the vectors, and you can check that out. The second equation is called the observation equation. And what it tells us is that YT, we don't necessarily get to see X, but we see a linear combination of the X's. And then the final thing is, and we always going to need this, we need an initial condition. This is an equation for the initial condition. And different people write down different equations, but we're just saying the initial X, which is the state, it itself is drawn from a normal distribution with some mean and some covariance. So this is the vision. This is the vision of the world, actually. And this would be Laplace's vision if we didn't have this shock process. See, Laplace was saying basically there's no shock process. Okay. Okay, so this is called a linear state space system. That's it. So the deal is, I give you the primitives of the model. So what are the primitives? To give you if I ask you, and by the way, this is a very homework-rich part of the lecture because it's very easy for me to make doable homeworks on. The primitives of the model is to specify a state space system, you have to give me this triple of matrices, A, C, and G, and you've got to check that the dimensions are what I told you. I have to give you a shock distribution, and I have to tell you about the initial condition. That's it. So I take these primitives, and what can we get from those? Well, we can do a lot in terms of simulating and analyzing the resulting system in terms of the xt, yt plus 1 process, the xt, yt process. See, what this is going to give us, it's going to give us it's actually going to give us a whole infinite sequence of xt, yt pairs once we start this thing out. And we can look at that sequence in a couple ways. One thing is we could view it as a random sequence. And it's a random sequence. What's it driven by? What's the randomness? We draw an X, and we draw this sequence of WT plus 1s. Draw that whole sequence. And where do we draw them from? Well, if you had a random number generator, if you don't know what that is, look it up in Wikipedia. Python has them. You take a random draw from the distribution of X, put it in, take a random draw of this, and then just plug it into these equations. And there, you've generated that sequence. In addition, and I'm not going to go into this, it turns out, since these are random variables, they have means and variances and other moments. And what do I mean by that? Every one of these xt's, for any particular t, x sub 100, x sub 300, y sub 220, and so on, has a mean and it has a variance. And furthermore, there are covariances between all of those. So actually, there's very convenient formulas for extracting all of those things just as a function of, you guessed it, those and those. We can get everything in sight just as a function of the primitives. So this is a machine for generating probability distributions of this thing. And since we're talking about that, I'll just tell you, I'll give you a free extra definition. Mathematicians have this notion called a stochastic process. And what a stochastic process is, it's just the probability distribution over a sequence. So if we have a sequence of these things, and we ask what its probability distribution is, and we know it, we've got a stochastic process. It's a fancy word. Okay. Okay, there's an explanation of something called martingale difference shocks. I'll come back to that. You can skip over this. So what this is going to say, this little part here is going to say the following. It's going to say the W that I've described is a martingale difference, but there are martingale differences that are more general. Okay, now, now what we're going to do is I'm going to move on, and we're going to do examples. And I advise you to write down these examples because they're going to be, you're going to see they empower you. Okay, so the idea is, the assertion here is, this is a key sentence: by the appropriate by the appropriate choice of the primitives, a variety of dynamics can be represented in terms of a linear state space system. That means by appropriate choice of A, C, G, U0, we can often actually forget these last two. By appropriate choice of these things, we can represent all sorts of systems. And the whole thing is, this is a kind of, finding the state is an art. Is going to illustrate this. And what does that mean? Finding the state, finding a definition of XT. So let's do a few examples, and then once we do a few, you'll get the feel for this. Okay, so here's an example. Here's our first example. It's a classic. Paul Samuelson wrote a very famous paper on this. It's one of the most, he wrote a pair of papers using exactly this equation, and then analyzing, oops, I just see a typo, analyzing it using methods that are less powerful than we're going to have today. This is called we're going to let YT be a scalar. It's a scalar deterministic sequence. So it's just deterministic, and it's going to satisfy this equation. It says YT plus 1 is equal to phi 0, it's a constant, plus phi 1 YT plus phi 2 YT minus 1. There's no shock. And Y0 and Y minus 1 are given. Samuelson showed that a multiplier accelerator system, one of the first rigorous Keynesian models, had this form. So if we take what Samuelson had and we want to map it into our state space system, how do we do it? Well, finding the states in art. Check this out. I'm going to define XT as equal to 1, YT, and YT minus 1. So YT is a scalar. I've mapped that scalar and a constant. You'll see why I put 1 in a minute. YT and YT minus 1. Now stare at this. What do I have on the right-hand side here? What do I have on the right-hand side? I've got all this stuff. I've got phi is a constant. I've got a constant hitting YT, and I've got another constant hitting YT minus 1. So just put all the things on the right-hand side into X, stack them up. And now what I want to do is I want to define a matrix A, a matrix C, and a matrix G, which maps this equation into this equation, xt plus 1 equals a xt plus c wt plus 1. If you check it out, and you could do this, everyone in the class I know, at least the people who've done in the homework, because I've looked at the homework, you're a lot better in linear algebra than I am. If you just check this out, you'll see that this works, because let's write this out. This is 1. Let's write this out right here. Fortunately, I have some room here. Let's write this out right here. I've got, what does this say? Copy 1 yt plus 1 yt. That's xt plus 1. Copy A. 1, 0, 0, phi 0, phi 1, phi 2. So this is 1 yt minus 1. Didn't plan ahead. And I copy 0, 1, 0. Now look, what this says, plus c is 0. So I just forget the c. C is just a vector of zeros at 0, 9. So what does it say? The first equation says 1 equals 1. That's profound, but it's true. Second equation says yt plus 1 equals, oh my goodness, phi 0 plus phi 1 yt plus phi 2 yt minus 1. That works. What does the third equation say? Yt equals yt. So those are all true, and they map. What have we accomplished? We've mapped this second order difference equation into a first order vector difference equation. Okay? So now you just think for a minute. I've mapped a second order linear difference equation into a first order vector difference equation. So I could ask you, suppose I had a third order scalar difference equation. Do you think I could map that into a first order vector difference equation? So instead of, I suppose I had this. You'll see where I'm going. Yt plus 1 equals phi 0 plus phi 1 yt plus phi 2 yt minus 1 plus phi 3 yt minus 3. See what I have to do? I just have to add some things to here and make this matrix bigger. So essentially any finite order linear scalar difference equation I can map into a first order vector difference equation. That's going to be very useful. Okay. And then actually, oh, by the way, this next figure, that shows why Paul Samuelson was interested in this. These numbers actually we picked here, they're very close to Paul Samuelson's numbers. And what this process will do, see, there's no shocks here, but what this process will do is it'll generate these cycles, these damp cycles. Okay. Well, so look what I have here. We're going to have now we're going to have a univariate third order autoregressive process. So look what we're going to do here. Here's our process. Yt plus 1 is equal to phi 1. Now this is third order. 1 lag, 2 lag, 3 lags, 4 lags. It's actually fourth order. I can't count. So now how are we going to define the state? Finding the state is an art. Define xt as equal to this. And that prime means transpose. And then look what our A matrix looks like. Oh, by the way, notice there's no constant here, so I don't have to have a 1. If I have a constant, I have to put a 1 in there. And then you can check out. I advise you to do this. This is empowering. Check out. Multiply this system with these definitions. Now I have a C because I've got this shock here. And that's the deal. So that's my univariate process. What about multivariate processes? Oh, by the way, look at this. Oh, by the way, a couple language. There's something called a companion form, a matrix. This matrix has a companion form. You'll notice it's got an interesting form. It's got these fees that do all the work for us, and down here it's got an identity matrix, and here's has a block of zeros. That's called the companion matrix form. No reason you have to know that, but it's pretty handy. Okay. So this is called the companion matrix to this vector. So this is, okay, if we take this system and we simulate it, notice what we get. We get this process that looks like this, and a lot of economic time series look like this. They have this property. They're erratic shocks, but there's some patterns in them. And famous economist named Slutsky, Russian economist, is kind of the first one to notice this. He took a system like this, and he noticed that he could pick the fees such that with just a single random shock, but a difference equation, what's called a stochastic difference equation, a stochastic linear difference equation, that could generate business cycles of the kind that we actually observe in the data. So the connection of Slutsky to this is very important. Actually, Slutsky actually showed is you give him cycles, and he'll produce a difference equation that will approximate it very well. Okay. So let's go on now. There's Christopher Sims and other people got very famous for writing vector autoregressions. Vector autoregressions. Well, we're going to show that vector autoregressions fit into our framework. So here's where we go. We're just going to take the previous example. See, linear algebra, we're working linear algebra very hard, and linear algebra is being very good to us. We're just going to take this example. We're going to amend it. Instead of yt being a scalar, yt itself is going to be a vector. How long? Go ask Chris Sims. He fits them for the Federal Reserve. He fits some pretty big ones. So he's going to write. He's going to write this. Yt is now a k by 1 vector. Phi j is going to be a k by k matrix, and wt is going to be a k by 1 vector shocks. If we do that, exactly the same, almost the same calculation we did before with one amendment. These ones now become identity matrices. They're I, k by k identity matrices. And the phis are now k by k matrices. And what we've done is we've mapped, and sigma now is a k by k matrix. So you could check out that this now is this now shows exactly what we had. It's exactly the same equation. I don't even have to rewrite it. It's the same equation, just a reinterpretation, where the yt's themselves are now vectors. So we just stack up all the vectors. How long is this vector? It's 4 times k by 1. It's a big, long vector, but it fits into our framework. Okay. I'll just keep going a little bit. So we can map. So what we've shown is we can map that object into our linear state space system, but we can map more. Seasonality. Like here's a crude model of seasonality. Let's go back and make it a scalar. This is as seasonal as you can be. Yt is equal to its value 4 periods ago. That's a deterministic seasonality, purely mechanical. What about indeterministic? Yt is equal to, it heavily depends on its value 4 periods ago, but there's a shock. Well, that fits. Here we go. How will that create? For our deterministic model, this is the model yt equals yt minus 4. our A matrix becomes this. Now here's a fun exercise. Compute A to the fourth. If you compute A to the fourth, it turns out to be the identity matrix. I'm getting lazy. Zeros. A to the fourth. Why do I have to do that? A to the fourth is equal to the identity. Okay, that's going to be useful. Okay, time trends. Suppose you want to make a time trend. How would you map that in? Suppose yt is equal to at plus b. Now here's an exercise, finding the state is an art. So if we stare at this, there's a constant and there's time. So if you check this out, this is kind of a challenging one. It's very fun. If you set a equal to 1, 1, 0, 1, c equal to 0, and g equals ab, and iterate that, you'll see it will recover exactly what we want. And then you could have also polynomial time trends. You can fit those. And there, the A becomes this. Okay. Okay. Now, if you have done some time series, there's something called the moving average representation. And how are we going to get that? We're just going to take this system that we have, and we're going to iterate it backwards. And if we do that, we can express xt as a, notice this is a matrix moving average of a particular kind of the shocks. So the state is composed by the history of the shocks plus an initial condition. Now that's really handy. So again, if you give me an A, a C, and a G, I can compute the moving average representations by doing this. Okay, and I'm going to stop here. If you've had time series, what a lot of time series is about is getting formulas for probability distributions of time series. And those go like, well, there's some very nice formulas for that. They're in this lecture. But I think we're really not going to need those for what we're going to be doing right now. So I'm going to okay. Okay, so here we are. I'm going to, we're going to talk about one of the most powerful applied math methods invented in the 20th century. It wasn't invented until after World War II. It was invented by two really smart people, Richard Bellman and Abraham Wald. And armed with the methods, there were a whole set of problems that very smart people couldn't solve. They're now routinely solved by undergraduates in engineering and graduate students in economics. First year in PhD in economics at NYU is all about this. So I'm going to talk about dynamic programming problems, and we're going to do a very powerful class of them that's cast in terms of the linear state space model. That's why I had to do what we just did. So it turns out that dynamic programming is it's easier said than done. It becomes very practical if you have linear quadratic problems. And so we're going to be watching where we have linear and quadratic in So here's where we're going to go. So our basic tool is going to be matrices, vectors of random variables. Okay. So there's going to be a linear part, and there's going to be a quadratic part that you should watch for. And so our artillery here is going to be knowledge of what a linear equation is, what a quadratic form is, and a little bit of linear algebra. Okay, so the first thing is we're going to have something called a law of motion, or a transition equation. Okay, so what's xt? It's a vector. Its length will depend on the problem, describing the state of some economic system. So what's a state? It's a complete description of the current position of the system. And we're going to assume that xt follows a linear law of motion. Now, this is just what we wrote down before, with one addition. There's going to be an additional thing called b times ut. And what ut is, it's a control vector. It's a vector of decisions that whoever's in charge of the system can make and alter the motion of x. So come into the system, you face an xt. You, the decision maker, choose a ut vector. Nature then draws these shocks, and next period state evolves. That's how it goes. And again, WT is just what we talked about before. It's going to be this sequence of shocks. So we're going to permit there to be shocks, and you're going to see in the consumption smoothing model that we're really interested in, those shocks are going to be important, and managing them is going to be important. Okay, so our dimensions. We have to do the bookkeeping. What is this about? This, you've seen this plenty of times. If you're going to multiply a matrix times a vector, you better make sure that that they're conformable. So B is n by k. U is k by 1. Okay, so let's take an example. We're going to consider a household with a budget constraint that looks like this at each t. It comes into the period with some assets, AT, and then it receives a risk-free interest rate of R. That's a net interest rate. So these are the interest earnings plus the original value of its assets. And then YT is going to be some additional non-financial income that it gets. So A is your asset level that you came in with. YT is your non-financial income. And what can you do with that? Well, you can consume, or you can save, or you can borrow. If assets are negative, that means you owe something. So one example is, if we assume that a simple example, if we assume y is serially uncorrelated and given by, and just has this distribution that it's normal 0, 1, then the law of motion is this, very simply. Okay, so now what we're going to do, we'll work with this example for a while, this very simple example. So, and you'll notice we've actually chosen quite a simple example because we know how to make YT serially correlated by using this trick that Paul Samuelson showed us earlier. So let's just do the following. We're going to take yt is equal to a constant plus a shock that looks like that. So we'll see what this looks like. It's some constant level of income, but just fluctuates around this constant with this random fluctuation. And now we're going to write down a utility function and a control. So we're going to define a state, or I'm sorry, we're going to define a control as being your consumption minus some level C bar. And I'll tell you what C bar is going to be later. It's going to play a role of bliss consumption. Okay, so now I'm going to use a trick. I'm going to write my law of motion for assets. I'm just going to add and subtract C bar, basically. So it's going to become this. My law of motion is this. This. There's my UT because it's C bar plus U. So take a look at that. Okay. So now I'm going to notice the following. If I transform that, again, finding the state as an art for this consumer, I'm going to define the state. Here's my state, xt. It's going to consist of assets and the constant 1. My control is this UT. And then this equation, that first equation gets translated into that. And if you'll notice, this is exactly the form that I need. What do I need? xt plus 1 is equal to axt plus but plus cwt plus 1. That fits like a glove. So I've given you matrices A, B, and C. So there's my definitions of the state, the transition matrix, my control matrix, my control vector, and my volatility matrix. Okay, so I'm half done for formulating my problem. I told you about the linear part. And now I'm going to tell you about the quadratic part. So in the LQ linear quadratic dynamic programming problem, there's going to be a loss function. Loss is a measure of stuff I don't like, or minus stuff I do like. So we're going to rig the mathematics so I can represent that as a quadratic form in a state plus a quadratic form in a control. Now, sometimes people also add this. They write out, we could also live with this, a cross product term. We don't need it for this problem, but the math would easily go through if I added this. So it would still be quadratic, but there'd be a cross product between the u and the x. But we'll leave that out for now. I'll just advise you, if you ever encounter a problem that has that feature, it's okay. And we're going to assume that R is a symmetric, non-negative definite matrix. And what that means is that this term is non-negative, and Q is non-negative. Q is going to be a symmetric, positive definite matrix. So what this term is positive. And what we want to do is we want to minimize it. Moreover, yeah. So, okay, we're going to actually want to do more than that. Okay, so this is just to remind you about, here's some simple examples. So what we're going to do is we're going to take a criterion function of this form for our little example. Okay, so our criterion function, our loss function, and notice this is a loss function in one period. We're going to have to add these up across periods later. But our loss function is just going to be ut squared, which is ct minus ct bar. So what that's telling us, we have some desired level of, we know what C bar is now. It's a desired level of consumption, and presumably, for me, it's a very big number. I'm way below it. So my loss is CT minus C bar is a big number. And if I could move CT up, I'd be happier. Okay, so now we're going to formulate an optimum problem. So we're getting very close to formulating our first dynamic programming problem, the first of the evening. Okay, so what we're going to do is we're going to assume that there's an individual, and he's going to live from 0 to time n, capital to time t. Okay, and we're going to formulate this problem carefully for a technical reason. Well, both for a technical reason and because it's going to make our life easier. Okay. So here's what the individual is going to care about. He's going to want to choose, what does he want to choose? He wants to choose a sequence of these controls. Well, so he's, the last period, he's kind of out of there. He's going to choose consumption C minus C bar and date 0, date 1, date 2, all the way up to the next to the last period. And what does he want to minimize? He wants to minimize, well, this is his loss function. We're going to add a discount factor, raise it to the t, and then we're going to have this terminal loss. And this is important to add. It's easy to forget about it, but if we don't, the math is going to come and tell us something pretty interesting. So this is the objective function. Now, we made it quadratic. It's a discounted quadratic, linear quadratic control problem. It's a quadratic objective function. So we want to minimize this whole thing, subject to our law of motion for the state. That's what we want to do. Okay. Now this is the mathematical expectation. So I'm going to tell you something about that. Don't let that scare you right now, because there's something remarkable about this problem, and that is we'll get the correct answer for almost everything we want by temporarily pretending that there's no C and no W and that there's no E. So if I do that, then there's no randomness, and this is now just a deterministic. These are just sequences of X's and U's, and this is just a sequence problem. Okay. Okay, now, so I want you to stare at this for a minute before the break. I'll make a couple remarks about it. The first thing is, if we stare at this and I ask you, from what you've learned at NYU and the master's program, do you know how to solve this problem? Remember, what's the person choosing? It's choosing these U's to minimize this objective function subject to these constraints. And there's one constraint for t equals 0 all the way up to t minus 1. That's what it is. So if I tell you you're going to minimize this quadratic function, it's just a big quadratic function subject to the sequence of linear constraints, could you do it? And what method would you use? So if I asked you to write down the answer, this is a constrained minimization problem. And you know a method for that. It's the method of Lagrange multipliers. And what you're going to do is you're going to form a Lagrangian to to add this thing up, and you're going to put Lagrange multipliers on every constraint. And how many constraints do you have? You have one for 0, 1, 2, t. So the method of Lagrange multipliers will work. It will work for this problem. So you already know how to solve this problem. And now that's pretty cumbersome, but it will work. So what we're going to do is we're not going to use that method. We're going to use, that method will give you the correct answer. We're going to use another method. Okay. Okay, so here's what we're going to do. We're going to use, and I think what we're going to do, this is a good time to take a break. What we're going to do is we're going to use backwards induction. And we're going to break, see, the method, here's the inspiration for this, and this is what Richard Bellman and Abraham Wald, two of the smartest applied mathematicians, or mathematicians straight out of the 20th century, what they saw. As I drive T to be very big, and they actually wanted to solve infinite horizons version of this, this becomes a really big problem. And you could solve it with Lagrange multipliers, but it would become really, really big. One really big problem. So they asked the following question: is it possible to convert this one big problem into perhaps a large number of much smaller manageable problems that I could solve sequentially, recursively? And the answer in this case is yes. That's their insight. If anybody, and actually, if somebody on the street asks you, I'll give you a choice. You got to solve either this one really big problem or this collection of much smaller problems sequentially. Always take the second. So that's what we're going to do. We're going to break this into a sequence of small problems. This problem has right before the break, I'm just going to draw you a picture. It looks like I have room for it right here. The way this goes, this problem has this, let's just ignore the shocks. So let's set the WTs always to 0, temporarily. They're not going to change this picture. They're just going to add one little feature. So here's kind of the deal. Here's what's going on. We're going to be given this initial condition. Okay. What's going to happen is you're going to choose a U0, put that in here, and then there's going to be an X1 that kicks out. And then you're going to get this loss, which is going to depend on X0 and U0 here. And then you're going to do the same thing here. At this time, you're going to pick a U1. That's going to kick out a U2. And now you're going to get a loss, X1 and U1. And the whole thing's just going to roll on. See how this is going to go? Okay, and those losses are those quadratic terms. And what you'll notice is, here's what Richard Bellman noticed. This UT, this U2, that influences future x's, but it doesn't influence past x's. And in particular, UT, that's going to influence future x's, xt plus 1, xt plus 2. It's going to have no influence on the past. So this is a particular kind of system. Our system is this particular structure. And Richard Bellman said, well, if I'm going to solve this problem, I'm going to work backwards. The system kind of naturally goes forward this way. Richard Bellman said, what I'm going to do is I'm going to start kind of at the end. I'm going to start at the end, and I'm going to solve for the last u as a function of the x that I was brought in, figure out what that should be, stare at that, and then work backwards. So you can solve the problem going backwards in time. And that converts one big problem into a whole bunch of little ones. And I think